So anyway, thanks to Edouard and Peter for inviting me here today, and I'm pleased to present some new biomarker-based evidence that the onset and the termination of the African humid period was relatively abrupt. And I'm showing this photo here. It's actually taken by National Geographic. This is from the Gulf of Aden. Some of the data I'm going to present today were collected from the Gulf of Aden in 2001 on one of the last oceanographic cruises in the region before the increase in piracy in those waters basically made oceanographic research very difficult. So we were quite lucky to collect these cores. Peter was on the cruise, and it's only just recently that we've completed analyses on these cores, and they've definitely told us something pretty exciting, I think, about how climate has changed in the Horn of Africa, where we don't have many traditional geological archives. So I think a lot of us here are here today to speak to this question of whether, in particular, the termination of the African humid period, that wet time in the Northern Sahara in the early Holocene, happened quickly or gradually. And I think that in large part how we define this, we're really talking about an issue of semantics, and I think we can't answer this question unless we define scientifically what does gradual mean and what does abrupt actually mean. So certainly we see evidence in geological archives of very fast changes. There's Peter's classic record here, which we've already seen a couple of times today. We also see evidence for more gradual changes. So this is a speleothem from Oman that shows, a generally gradual shift from conditions of high precipitation to low precipitation on the Arabian Peninsula. So what I'd like to do is actually change the conversation by defining this as a scientific hypothesis, and we are scientists, so I think this is the way to go. And I'm going to choose as my null something pretty simple, which is that the duration of the termination of the humid period is indistinguishable from the change in the primary forcing, which is the change in orbital forcing over the last 10,000 years. So if there are no feedbacks operating in the climate system, then we expect our proxy data to look like this, basically to follow the change in orbital insolation since the early Holocene. And if we go to that data and attempt to detect a change, we would find that the duration of the change is 10,000 years. So that to me is what gradual means. Gradual means there's no feedbacks operating on the system. And I think feedbacks are really what we're concerned about from the climate sense, because we want to understand what sort of things amplify the climate changes in the desert ecosystems that we're looking at, and whether that be vegetation changes or dust or ocean atmosphere feedbacks. Those are important to define, and of course they have implications for early human civilizations as well. So I'm going to define that as the null hypothesis, and I'm going to test it using two marine sediment sites from either side of North Africa. The first site that I'll talk about will be this site from the Gulf of Aden, and you've already seen some of these data today. And then I'm going to move over to the other side of the Sahara and present some very new data from this marine core, GC68, which sits off of Mauritania. So the primary indicators that we're going to use for past changes in aridity in this region come from the study of molecular paleoclimatology, or biomarkers. And what this is sort of my discipline, I guess, and what it is using fossils, but not just, not the hard fossils that we're used to, but actually molecular fossils that are preserved in sediments and lake sediments and ocean sediments, and tell us about how past climate has changed. And we can actually learn an extraordinary amount of things about how past climate has changed from these indicators, including precipitation, temperature, vegetation change, PCO2, and the list goes on. And one of the reasons that this technique works so well is because biomarkers are really well preserved. So when you think about, it's a morbid question, but think about what is the part of your body that would last longest after you die? Okay, well, so most people would say bones, right? Because that's what we think of as fossils and bones, but it's not actually true. The thing that lasts longest after you die is your cholesterol. So your fat will outlive you even when your bones have turned to dust, unfortunately for us all. But fortunately for geologists, we can find remnants of fat everywhere, going back literally billions of years. So this is cholestane. It's the geomolecule version of cholesterol, and we find this in primordial Precambrian rocks. So this is something that just never goes away. We can find fats in everything. And because of that, we can use fats to reconstruct climate almost anywhere on Earth. So today, I'm going to use a particular kind of fat indicator or biomarker that comes primarily from higher plants, and that is the plant leaf waxes. So Edouard already introduced these earlier this morning. These are quite literally the waxes that sit on the leaves of plants. They are ablated by wind and water and then moved into sedimentary systems. And they're very simple molecules. Alkanes are, in this case, I'm going to be using the carboxylic fatty acids that are also ubiquitously made by higher plants. What I'm going to do in particular is not just look at the distribution of the leaf waxes, but actually the isotopic composition of them. So we're actually going to measure hydrogen isotopes on those leaf wax molecules individually. And the reason we do this is because the hydrogen isotopic composition of the waxes is a direct indicator for aridity on the landscape. So this is a little schematic about how that works. So what we're measuring is this is our molecule, and we're able, using GC coupled to isotope ratio mass spectrometry, measure the isotope composition of it in terms of per mil notation. But what it represents is this sort of system of things that happen on the landscape. So if we start from the rainwater, ultimately the plants are using water in their landscape to make these waxes for their leaves. The hydrogen comes from the water. So we start with rainwater, and we're in the tropics, so let's say it has an isotopic composition close to 0, close to what you would see from mean seawater. We enrich that water or lose some of the light isotope through evaporation processes in arid environments, also through transpiration in the plant leaf. So as that water gets taken up by the plants and then moved into the leaf, of course, the lighter isotope leaves the leaf stomata through evapotranspiration, and we end up with a pool of water that's a lot more enriched than what we started with. But then the plant fractionates as it uses that water to make its waxes. It sort of discriminates against the heavier isotopes, as biological systems typically do. And what we end up with is a sort of something around a minus 100 per mil. So the difference between the rain and the wax is what we call the apparent fractionation, or epsilon. And that's generally constant, but of course it does change whether you're in a more arid or humid environment. So we really use this right now as mostly a qualitative indicator of past aridity or humidity, in the sense that when we see more enriched values of leaf wax isotopes, we can infer that the landscape was more arid, and that would increase evapotranspiration and also the source water deuterium. Whereas when the value is more negative or more depleted with relative to deuterium, we see that we're looking at a more humid landscape. So that's sort of the paradigm that I'm going to interpret the data that I'm going to show you today. And I want to start with our Eastern African site, this marine site that is sitting in the Gulf of Aden, collected in 2001, as I said previously. And I think it's a great site to look at leaf wax compounds in particular, because most of the terrestrial organic matter here is delivered by aeolian processes. There's really no major river systems that dump into the Gulf of Aden. And we really have this single peak of dust flux into the Gulf of Aden every year, which is in June, July, and August, when the Indian monsoon winds sweep over the Horn and deliver that dust right into the Gulf. And so most of our organic matter is coming from the Horn and the far regions rather than Saudi Arabia. So we really are seeing that Horn of Africa signature in the terrestrial organic matter. Okay, so here are the data. And you've seen this before. So this is now I'm plotting time in the Paleoceanographic sense, which means old on the right and young on the left. And so and here's our leaf wax values. So up, more negative is wetter on this graph. So we can see that this record actually goes back a little bit farther in time than some of the records that we've shown today. It goes 40,000 years ago. What we can see is the last glacial maximum is here. It was quite arid. But the most arid time of the last 40,000 years was definitely this millennial scale event here, which is called Heinrich Event 1, and that's associated with North Atlantic cooling. We have this sort of two-step deglaciation, which is very classic, into the Bowling-Ailerod warm period, back down to drier conditions in the Younger Dryas, and here's our humid period right here. And so I think you can see by eye that as we moving in and out of the humid periods actually happens pretty quickly. But I think we can do better than that. We can tell you how quickly that actually happened. By the way, the error bars here represent a couple of things. They represent the analytical error on the isotopes, but also the age model error. So as Edouard mentioned earlier, we cannot date these archives precisely. There's going to be some uncertainties, and I'm going to use a Monte Carlo method throughout this talk to iterate through those uncertainties so that we can sample them and get a better idea of the timing and the duration of these transitions. Okay, so the fact is we actually see similar evolution in leaf wax records all throughout East Africa. So these features are not unique to the Gulf of Aden site, and they're not unique to marine sites either. So I've previously worked in 2 lake systems, Lake Chala, which is here on the slopes of Kilimanjaro, and Lake Tanganyika, the Rift Lake. And we've measured also leaf wax isotopes. So the nice thing about this proxy is you can do it in terrestrial environments and marine environments. And you can see that they all have similar transitions. These 2 records in particular look very similar from Lake Tanganyika and the Gulf of Aden, even though they're thousands of kilometers away. So there really are these large-scale hydrological features that span large geographical areas. I've highlighted the abrupt transitions that we see in these data sets in red, which are actually detected using a change point method. And just, again, comparing to the orbital curve, you can already see that they're happening faster than that. So what we can do is iterate the age model uncertainties in each record and make probability distributions of the duration of each of those transitions. So I'm showing you the 3 transitions here: the termination of Heinrich event 1 into the Bolian-Alrod, which is the first step towards wetter conditions in East Africa, the termination of the Younger Dryas, which is sometimes thought of as the initiation of the African humid period, and then the termination of the African humid period. And I've just labeled the humid period termination distributions here. So this is what we see when we iterate the age model uncertainties. We see that the Aden site, we're looking at a termination that's somewhere around 900 years, a little bit longer at some of those lake sites. Now, what we have to think about when we actually interpret the duration of these changes is the influence of sedimentology. So what we see in these sediment cores is actually a fairly consistent relationship between the inverse of the sampling rate, or how finely you sample the core, which, in other words, the sampling interval and the duration. So actually, sampling interval combines 2 things. It combines how finely you sample the actual physical core, but also the influence of sedimentation rate and bioturbation. In other words, what we're looking at is how the signal gets aliased when we measure it in archives that look like this, right? So none of these archives are perfectly laminated, far from it, especially in marine environments. And so, of course, we're going to be averaging out some of the climate signal. So the degree of aliasing really depends on how fast the sediment accumulates and how finely we're sampling transitions. And that's exactly why we see this relationship here. Now, because this is here, we can infer that these probability distributions are actually maximal estimates of the duration of change. So in all likelihood, it's very, very likely that the duration of these events happen much, much faster than that. So I think the challenge before us is actually how do we back that out? How do we get that number of what the real duration of these really dramatic transition was? And I'm going to sort of do a back of the envelope thing in this case of these 3 sites, use this relationship to correct the values for their slope contribution and end up with probability distributions that look like this. So you can think of this as a theoretical estimate of what the actual climatic transitions were. All right, and when we do that, when we correct for the sedimentology, we now see that our humid period transitions are, in most cases, on the order of hundreds of years, maybe a little bit longer at the Tanganyika site. So now, I remember I set our null hypothesis with 10,000 years. So even with the observed distributions, we can definitely reject the null hypothesis. Okay, we're not seeing durations that are 10,000 years. There's no way. And it was probably a lot faster than that. So I think for the East African region and Northeast Africa, through the Rift Lakes, there's plenty of evidence out there that suggests that the termination was relatively fast. Certainly, it was faster than the orbital forcing. Okay, so let's move over to West Africa. So I'm going to show you some new data from this site, GC68, which is actually close to Peter's original site, ODP 658, where we measured dust fluxes. Obviously, this is a great place to measure dust flux, as you can see. But I'm going to show you leaf wax data. And so this is the leaf wax record from West Africa. And this is literally, I just finished running on this on my mass spec like a week ago. So this is the first time I've shown it. And we can already see some familiar features for sure. We see our sort of deglacial sequence where we have a relatively arid LGM, and Heinrich 1 may be less well defined than in the West. a very depleted or wet Bolignala here at the site, clear Younger Dryas, and then here's our human period, which noticeably has this sort of decline around 8K, similar to what Edouard was talking about earlier. And here's our transition out of the human period. So these are our radiocarbon dates, and again, the error bars represent the compounded analytical and time uncertainty. When we compare this record to what we found in the east in the Gulf of Aden, you can see that actually the signal is much smaller, which is sort of interesting. So we see a very large isotopic signal in the Horn of Africa, but much smaller range of change actually in this West Africa site. So, and some similarities, but some, of course, differences in timing. In particular, perhaps the termination happened a little bit later. We'll look at that in more detail in the West African site. So going back to our sort of sampling, or I guess our sedimentation rate effect, we can ask, do we see that in the deuterium data from GC68? The answer is yes, but the mid-Holocene, or the termination of the African humid period, which is here, plots off of this line a bit. So this is actually maybe somewhat to be expected. If that termination happened a lot slower in West Africa than East Africa, you would expect it to plot above that line. But it may also indicate that the relationship between sedimentation rate and the duration of events is a little bit different for this lower sedimentation rate marine site. So just as an experiment, though, we can use the same regression technique that we used in East Africa to have a look at the observed and the theoretical duration of the termination of the humid period, and in the observed space, again, talking around 1,000 years for the East African sites. So longer at our West African site for sure, closer to 2,000 years. And then in theoretical space, that would put the duration of termination more around 1,500 years or so for the West African site. So, you know, it's a little different, but still faster than 10,000 years. So the nice thing about the GC68 site is we have a couple other of measurements that are indicators of aridity besides the leaf wax isotopes. So we can kind of confirm whether the patterns we see in the leaf waxes are similar if we measure something else in the same core. So the leaf waxes are on top here. Here I've got another molecular indicator for runoff, which is called the BIT, or BIT index. This is a ratio of a group of compounds that are thought to be primarily terrestrial derived, branch, glycerol, dialkyl, glycerol tetraethers. It's a mouthful. It's a ratio of those to isoprenoidal GDGTs, which are mostly produced by marine archaea. So it's just a terrestrial to marine ratio based on biomarkers. And actually, we see it really nicely captured similar climate changes, very prominent Younger Dryas. Here's a humid period. Here's the transition out of it. Looks similar, some differences though. And then finally, dust flux. So David McGee has measured a dust flux on a sequence of cores all the way up the West African coast, and this is the record that he published from GC68. We see very, very prominent increases in dust flux during those millennial scale events, again, Heinrich 1 and the Younger Dryas, and reduced dust flux during the humid period consistent with wetter conditions, and again, a transition out of that. So we can just, play the same game, iterating through the age model uncertainty to compare between proxies, what did the observed duration and the midpoint of the transition actually look like. Observed durations, we're starting to see somewhat consistent results between each proxy, although dust seems to be a little bit faster. And when you think about what these proxies represent, that makes sense. The response of dust to aridification may be slightly more nonlinear than what you would see with a runoff proxy or an isotopic indicator. Midpoint of the transition, so there are sort of sedimentological-esque indicators here, have a similar transition midpoint of around 5,100 years or so. Delta, so the deuterium actually has a later change, which I think is kind of interesting. So there seems to be some differences in the isotopic signature from the terrestrial proxies. And this is just, again, something you can do if you actually take into account the age model uncertainties and play this game. You can learn about leads and lags between different proxies and what that might mean for the climate system. All right, so I'll also show you the same plots for the onset of the AHP, just in case it's of interest, or the termination of the Younger Dryas. Here we see a slightly faster observed duration of around 1,000 years, maybe 900, 800 years. And in this case, all three proxies basically agree on the midpoint of the transition, something around 11,700 years ago, which is right in line with the termination of the Younger Dryas in the northern hemisphere. So so the bottom line here, though, is that no matter what you do, no matter what sort of statistical games you play, we can reject our null hypothesis. There's no evidence in any of these data that the termination in West Africa was 10,000 years. And so by that definition, we can call it abrupt. Now, if you want to change your null and say that abrupt means it has to have happened within 500 years or 300 years, that's fine, and we can test it over. And if you set your null like that, then yeah, some of these proxies may not agree with that. But I think in terms of climatic forcing, we have to understand that there are some feedbacks operating in the climate system, for sure. And so what you have is, the insolation curve, and just as a representative average, this is the first principal component of all the leaf wax data from East and West Africa. And this is basically the composite curve that we get. It's very characteristic, 2 steps out of the last glacial maximum. In some places, this Boreal period is a lot wetter than others, which I think is interesting. There's some spatial dimensions to that. We see the Younger Dryas as dry event, and then in a lot of these records, we see a sort of a mid-Holocene decline right around 8K. It gives a sort of characteristic M shape to the data. And then there's this transition here. So, by this definition, I think the termination of the humid period was abrupt in most places in North Africa. But abrupt can mean like 1,000 years, because that's an order of magnitude faster than the orbital forcing. Okay, and I'll just add that we're working up data from these other sites off the Western Sahara that were part of the same cruise in 2007, and I'm running these numbers right now. So we're actually going to have a nice latitudinal transect of how the leaf wax, the biomarkers, and the dust all the way up the Saharan coast. And these are the locations of the other sites that I just showed you today. So just for the second part of my talk, I want to talk a little bit about climate dynamics and some of the mechanisms that we might seek out to explain why the changes in the humid period don't happen gradually. Why do we see these nonlinear changes? Something has to be happening in the climate system to make a slow change in orbital forcing manifest as a faster one. So I think the classic mechanism that we're all familiar with is the vegetation feedback, or the so-called Tierney mechanism. And that's the idea that as you change the vegetation on a landscape, the surface albedo affects the climate. And so there's a feedback there. And as you change the albedo, you're going to change the rainfall and the precipitation regime. And so this has been floating around for a long time as a feedback mechanism for North Africa and possibly for East Africa as well. So I'm going to look at this actually now just for actually this whole conversation that's about to happen will be just for East Africa, primarily Northeast Africa. But we can apply these same techniques to our West African sites. I just haven't done it yet. So what we can do to look at past vegetation change from the molecular perspective is look at the carbon isotopes measured on those same leaf waxes, which in Africa are a fantastic indicator for ecosystem. So not just C3, C4 plants, but in fact, you see that as you move across the spectrum of leaf wax delta C13 values, we move between these different ecosystem types. So in grasslands, we see this very enriched value, so we're minus 22 in our leaf wax lipids. As we move through the woodlands and into the forest, we get to almost, over 10 per mil, or 15 per mil difference. So these are huge changes in carbon isotopes. So we can use the carbon isotopes as a rough indicator of what our ecosystem looked like through time. So I'm going to do this for each of the 3 sites in East Africa where we have paired carbon and deuterium measurements. And we're working on measuring carbon on the West African sites, but I haven't done it yet. So I'm color-coding the data by the biome, and I apologize that the yellow part is a little washed out. At Lake Tanganyika, we see a huge change in carbon isotopes through time, about 10 per mil. So today, we're seeing this light, sort of light tan that's consistent with a sort of open woodland forest. Perfect. That's exactly the environment that's around the lake. As we go back to the early Holocene, though, we see the development of a more humid forest. And this is entirely consistent with the pollen evidence from Lake Tanganyika as well. So when we move from a humid forest out to a much more open landscape, that's a fairly large change in landscape. So it's possible that we could see a vegetation feedback perhaps kicking in and explaining why the deuterium has this very abrupt shift. But note that the landscape does not. So the landscape is changing very gradually, but nevertheless the precipitation is changing abruptly. And that's a pattern that we see a lot of places, I think, as Florence was sort of getting at. Moving to the more arid sites in East Africa, we see much smaller changes in carbon isotopes. So in the Gulf of Aden and first, note the scale, we're moving just about 4 per mil here, mostly between the browns, so between grassland and woodland. And again, remember that a lot of the catchment here is actually just desert, so you probably have a few acacias and not much else. So you see, that it's sort of evolved between these grassland, woodland, sort of scrubby ecosystems through time, and hasn't changed in any consistent way in relation to what the leaf waxes tell us, the deuterium tells us about the hydrological cycle. Certainly there's not a big shift at the termination of the humid period at all, maybe 1 per mil. So I don't think that we can invoke a vegetation feedback for this particular region. Same thing in Lake Chala, we see much more sort of grassy, arid conditions at the LGM, but in the Holocene it's actually pretty consistent. So we have the same values throughout. So I think in these more arid sites, actually, the vegetation feedback becomes a little bit hard to defend if we think that the landscapes didn't change all that much, at least at these 2 places. So if it's not vegetation, what else can we draw on to understand rapid change? So I've been doing a little bit of work trying to understand whether the ocean atmosphere system itself can account for some of the more nonlinear changes that we see in the climate records in East Africa. And this work is motivated by research that we've done on much shorter timescales, looking at the role of the Indian Ocean in driving decadal scale climate changes in East Africa. So this is sort of in the last millennium, but now that we're going back farther in time, the similar sort of dynamics can apply. And what we found in this work was that on lower frequency timescales, the influence, this is a correlation of rainfall in East Africa with SSTs, or sea surface temperatures globally. On the annual basis, we see this classic correlation pattern that's associated with the El Nino Southern Oscillation System, which drives heavy rainfall on the Horn. On the low-frequency timescales, we actually see that the tropical Pacific influence completely drops out, and what's left is the Indian Ocean. So it seems that when Indian Ocean SSTs are warm, it's rainier on the Horn, and then, or conversely, when Eastern Indian Ocean SSTs are cool, it's rainier on the Horn. And this is related to changes in the Walker circulation, atmospheric circulation over the Indian Ocean. So this sort of gives us a clue, well, maybe we should look into the thermal history of the Indian Ocean over the humid period to see if it has any relationship to what we see in our hydrological proxies. So to do this, I'm going to go back to my biomarker toolkit again and pull out some new tools that are used to reconstruct sea surface temperature. So I'm actually going to use 2 techniques that are based on lipids produced by different groups of organisms in the ocean. So one of these proxies, TEX86, stands for the tetraether index of 86 carbons, is based on the relative cyclization of, again, these GDGT molecules, or glycerol dialkyl glycerol tetraethers. And the other, which is called UK37, and that's because it was developed in Great Britain, it has nothing to do with the actual chemistry, is based on the relative unsaturation of these long-chain ketone compounds. Both of these proxies are based on the same physiological adaptation that microbes have to temperature, which is that microbes change the structure of their lipid cell membranes in response to the temperature of the water they're living in. So in the case of the GDGTs, when it's cold, we see that the organisms produce compounds without any rings, and as it gets warmer, they add rings. And the analogy with the alkanone lipids is that at cold temperatures, they have more unsaturations in the lipid membrane, and then at warm temperatures, they have less. And you can understand that very simply if you consider butter and oil, which are 2 fats that we're very familiar with. Oil at room temperature is a liquid. Butter, obviously, is solid. Why? Because oil has more unsaturation. So this is exactly what those organisms are doing. When it's colder, they're going to put more unsaturations or less rings into the lipid structure to maintain that liquid crystalline state and the proton gradients they need. And when it's warmer, they're going to move to a saturated state. So you can think of it that way. And that's why this works in a lot of different lipid classes. Okay, so these are the data. I'm showing you actually 3 proxies. I didn't talk about the third one, which is based on foraminiferal measurements of magnesium-calcium values in 018. Peter might mention that later. But here are our lipid proxies, TEX and UK. And so you see they bounce around a lot. I mean, we're getting temperatures of around 27, 28 degrees in the Holocene, which makes sense depending on the proxy you set. Some differences in the deglaciation, and in the text is actually much cooler in the last glacial maximum. Now, there's a lot of interesting differences in the proxies here that I think say things about where they live in the water column and what they're recording. But for now, I just want an average value. So what I'm going to do is actually average these all together using a Bayesian approach to make a master curve of the thermal history in the Gulf of Aden. So I'm using information from all 4 proxies in a Bayesian framework here to produce this sort of cloud of possible temperature values going back through time. And that's what we see here, and the white is the median. So I'm not going to talk too much about the structure here. I want to focus on whether or not any of this temperature history might have influenced, again, the dynamics of the humid period in East Africa. And to do that, I'm going to compare it to a temperature record across the basin off of Sumatra, where they have 3 proxies, not 4, but I'm going to use the same technique. And so now we've got a history from here and a history from here, so maybe we can look at the east-west gradient and see, has it changed through the last 20,000 years or so, and does that relate to what we see on land? So, oops, too fast. There we go. So this is the result, and I'm just plotting the median value of the east to west gradient in blue here. The east is today warmer than the west by about ½ a degree, so that's right where we want to end up. And you can see that according to those 2 proxy records, there's been large changes back through time. So up would be a reduced gradient, which we might expect to correspond to wetter conditions. So actually what we see is a pretty strong gradient today and in the LGM. And actually the weakest gradients fall during the deglaciation, which is in part because the Aden site warms earlier than the Eastern Indian Ocean site. But focusing for a minute on the Holocene, it is true that, at least according to these 2 sites, that the gradient was reduced during part of the African humid period, for sure. It's sort of this gradual change now from about 10,000 years to present. So we do see evidence for less of a gradient in Indian Ocean SSTs, which would be consistent with the hypothesis that perhaps the ocean had something to do with feeding that humidity into East Africa. Of course, we don't see any abrupt shifts that happen at the same times or anything like that. So I don't know that it's a perfect smoking gun, but it's certainly moving in the right direction. So I think this leaves me thinking that, well, okay, maybe the ocean matters, but it's probably still not enough. There's got to be something else going on to explain why these changes are fast. And the one factor that I would really like to look into further is actually dust itself. So dust has a huge effect on albedo. It has a huge effect on atmospheric circulation. And I don't think we've really looked at in our community actually the radiative impacts of when you kick in Sahara dust into the atmosphere, which we did in a major way about 5,000 years ago. So I'd like to encourage the climate modelers in the audience to consider using interactive dust modules to investigate the impact that dust might have on nonlinear changes in climate in North Africa. And with that, I'll take questions if I have time. Thank you.